fall, that means you're using the acceleration due to gravity. Does that make sense, guys? Hello?
Yeah.
Yeah.
So again, right? They gave you the
Entire
acceleration here.
function.
If they don't
So
give you the
whatever f of
acceleration,
x is,
they're
now you're
implying
going to
again that
negate
they're
it,
using
and you're
acceleration due to
going to get
gravity, and then they will not give you the A, and
you're
then
going
you
to,
have to
if you
go back
negate
and say,
it,
oh my
in this
gosh, I'm
case, if
supposed
you
to use
negate
A,
x squared, you're going to get
right?
negative x squared.
And then again, you
Please
solve,
remember
and then you
the
get your
black
answer, and I
parabola,
have to write my unit. So again,
x
formula,
squared, that's the parent
substitution
function.
with
So we're starting
units.
out with the
Do
parent
not.
function to make things easy. And if you negate the whole thing, instead of having this x squared, you end up with negative x squared, which is simply flipped over the x-axis or reflected in the x-axis. Okay, and that's all that happens there. Um, that's one way to do a reflection. There's another type of reflection that we're also going to see, and that's a reflection in the y-axis. So now instead of flipping it up and down, it's flipping it this way. Okay, it's flipping it this way, left and right over the y-axis. Okay, so now to reflect on the y-axis, you don't negate the whole function like you did in the x-axis. You simply negate the x inside. So if you do that, this x becomes negative x. You're negating the x, you get negative x. And if you take negative x and square it, well, then you got positive x squared again. You're back to what you started with. So the reflection and the original are the exact same function. That's interesting. And there's a reason why that is. If you think about the graph of x squared, it's actually symmetrical about the y-axis. So when you reflect it, okay, the left side sits exactly on top of the right side and vice versa. So you don't really see anything because the graph is a mirror image of itself. When you do the reflection, it's sitting on top of itself. So you have back your original. And this is also seen in algebraic form. When you actually perform the algebra, you see that the reflection is the exact same as the parent because of the symmetry that exists between x squared and the y-axis. It is not symmetrical about the x-axis, and that's why you get a new function when you flip it over the x-axis. It's because it's not symmetrical there. Um, that's basically it for reflections. There are other types of reflections, but we're not going to talk about those today. We'll talk about a reflection in the line y equals x, which is more advanced, a little later in the year, but we're not going to worry about that now. Any questions on reflections in the x or y axis? Anything at all? Okay, so if we're okay there, I'm gonna continue forward and again, when you get questions like these, it's actually okay to simply use Desmos and you can see it for yourself. So let me show you that really quick. I want you to see this in practice. Let's go to Desmos so we can get to see this in action here. Okay, let me give Desmos a chance to load up. Okay, it should be loaded up now. And in purple is basic old x squared. There's nothing with it there. It's a parent function. And I want to show you negative x squared, which is the first thing we did. It should flip over the x-axis. Negative x squared. So my parent function's in purple, and my reflection is in blue. And you can see when you negate x squared, I get the reflection over the x-axis. Okay, so that's what happens there. Um, if I do the reflection in the y-axis, which would be negative in parentheses negative x squared, you'll see that the green function is sitting on top of the parent function because this and this are the same. Okay, they're the same thing. The reflection in the y is the same as the original because x squared is a mirror image of itself when you reflect through the y-axis. In other words, it's symmetrical, and that's why we get this. So let me go back now. to Notebook. And
I have a question.
yes, question, sure.
Will there ever be an exponent inside the parentheses?
Will there ever be another exponent inside the parentheses? Um, yes, there can be when you're substituting in something that's more complicated. Yes. In this activity, though, I don't think I have anything complicated like that. These are just going to be values. Like it's either going to be a numerical value like two or a half, or a negative symbol. We're not going to have any other exponents in these. When we do polynomial functions, that will change, okay? But so in this chapter, the answer will be no. In the next chapter, the answer will be yes. All right. The reason is this chapter here is strictly about quadratic functions only. And if you start to change the exponent inside, then you end up changing, you won't have a quadratic anymore. For example, if you have x to the third or x to the fourth or x to the fifth, that's a higher degree polynomial function, and that's no longer a quadratic. Those matter, they are important. They're so important they get their own separate chapter. Okay, but for this chapter, for this unit, it'll only be quadratic functions. So when you take test two, there won't be anything with higher order, with higher degree exponents, not until the third exam, when then there are. Okay, so for this, we're only going to be substituting in numerical values or negative signs, and that's it. We're not going to be putting in, like higher order, higher degree exponents. Okay, so so basically we have these covered. Now we're going to look at horizontal stretches and shrinks and vertical stretches and shrinks. And I'm actually going to come on the right side here first. I like to talk about vertical first because vertical are the ones that are logical. Horizontal, everything's backwards. Whenever we're doing horizontal, it's always everything's backwards. Adding it moves it left, subtracting it moves it right. Everything's like reverse. So vertical, everything is what you'd expect. So for vertical, we're starting out with a regular old parent function. It's in black ink, x squared. There it is. Okay. And now we're going to multiply f of x by a value, a. So yesterday, I gave you this formula, and I altered h and k. What I did not touch is A. I did not touch A yesterday at all. Okay. So today I am going to manipulate this function of the A value. So the A value, when we change this, this actually results in stretches and shrinks. Okay. This is not a translation where it just shifts it around the coordinate plane. By manipulating the A value, by manipulating A, you stretch or shrink your parabola. Okay. We know that H is just a horizontal shift from yesterday. And we know that K is just a vertical shift from yesterday. Okay, and this is all in your notes yesterday, these two items. So the only new piece is the fact that now I'm tampering with the A value. I did not touch A yesterday at all. I only like to introduce, small pieces at a time. So now we're actually going to be touching the A value, okay? And there are two things that can happen. There's a difference between vertical and horizontal. Vertical, the A is multiplying the entire function. With horizontal, the A is multiplying the X inside the function. So these are not, okay, they're not the same activity, all right? They're different activities. You're multiplying the whole function by A, that's going to be vertical. If you're multiplying just the X by A, that's going to be horizontal. The same was true yesterday to a degree. When you add K, you're adding it to the entire function. When you tamper with the entire function, it's a vertical change. When you just do something to X, subtract or add directly to X, that's some type of horizontal change. So that's going to be true throughout the activities. All right. Whenever you change the whole function by adding, subtracting, or multiplying or something like that, you're going to be doing something That's a vertical change. It's some type of vertical thing that's happening. When you tamper with the x value inside the function, all right, that's going to be some type of horizontal change. Okay, so those are two things that I kind of mentally know. So that gives me, it allows me to solve these problems a little faster. I have an idea of what's happening based on that. Okay, so I'm going to take care of the vertical first. So I'm multiplying the entire function by a value. So let's do a value like, I don't know, how about y equals 2x squared? If I do 2x squared, well, 2 is a number that is greater than 1. So 2x squared might look like the blue one. Because 2 is a number bigger than 1, I am vertically stretching my graph. In other words, my graph is moving away from the x-axis. It's stretching away from it. And a vertically stretched graph, it looks taller and narrower, or more thinner than the parent function. Okay, so that's what's happening here. This is a vertical stretch. Just to make sense of this, if I were to do 3x squared, it would get even taller and narrower. If I were to do 10x squared, it'd be even more narrow and even more like, like tall. So basically, as you make A very large, the graph becomes more stretched out. It gets more narrow or thinner, and also like elongated, taller. In other words, it's moving away from the x-axis. All right, that's what a stretch does. Now, what if you want to make a vertical shrink? Well, to shrink A vertically, we have to use small numbers or numbers in between 0 and 1. So an example of something like that might be a half x squared. Okay, a half x squared, okay, that's a number between 0 and 1. It's smaller than 1. And that might look like the red one, okay, where this graph is getting wider. It's a vertical shrink. A vertical shrink means it's not as tall. So when it's not as tall, it's getting pushed towards the x-axis. It's getting wider. So this is a vertical shrink. Let's explore this in practice because I know these can be hard to remember, and that's okay. We don't have to memorize them like that because we have Desmos as an application, which will allow us, right, to visualize everything here. That's kind of the point. So the calculator is super helpful in this. You really want to take advantage of Desmos here. This is where Desmos really shines in these types of questions. So let's explore this concept further in the calculator so we can see what's happening. I know people don't like sitting around trying to memorize formulas. That's really not a lot of fun. And I don't blame you. So I want to take a look at what's happening when we start playing around with values. So let's see. Let's try doing 2x squared. 2, 2, oops, 2x squared. Okay, you can see that this one, right, is taller, right, and not as wide as the parent, okay? Because I put 2x squared in. If I put 3x squared in, 3x squared in, okay, this black function, right, this new one, is even more narrow and taller. It's vertically stretched even further compared to the parent function, which is it's like a purpley color. Let me get rid of this because it looks the same. So the purpley color one's the parent. What if I do 5x squared or 10x squared or something like that, make it even bigger? Okay, now you can see 10x squared, okay, is even pulled, it's vertically stretched even more. It's pulling away from the x-axis. In other words, it's getting taller and thinner or more narrow compared to the parent function. If I put 100x squared in, curious how that would look. Okay, now it's like super stretched. Okay, it's very tall. It gets tall very quick. It's very narrow and it's pulled away from the x-axis greatly. That's stretched out vertically very much because 100's a pretty decent sized number compared to these other numbers. It's pretty big. All right, what if we start using smaller numbers that are in between 0 and 1, like a third? If we do that, You see the graph is getting wider. It's vertically shrinking. Okay. It's getting closer to the x-axis. It's getting wider. Okay. It's a vertical shrink. It's not as tall as the other ones. I can make it even flatter. If I do 1 divided by, let's say, 50 x squared, that should be really wide. Okay. So 1 over 50x squared, that's this. You can see this is pretty wide. All right. It's vertically shrunken. Okay. It's getting closer and closer to the x-axis. Any questions on what's going on here with the relationship? Anything at all? I can only, we're okay then? I'm assuming that we're okay. All right, so
Yeah.
oh, great. So that's what we have so far. And this is why I like the calculator. You can visualize it for yourself. So if you forget, oh no, I'm not sure what the property is, well, no worries. You can figure it out just by dropping, values into the computer and then looking at it. So that's always a great way. You can see what's happening. I like the visual. For those of you who just like to memorize the formula, then that works too. That way always works. But I think it's a good idea to have an understanding of like what's happening visually. I find it makes it so you have to remember everything all the time, that you can figure it, you can reason it out. Okay, so that's all I have for that part. Let me go to the thing next to it, which was horizontal stretches and shrinks, and we'll talk about those. Okay, so now we've talked about vertical stretches and shrinks. Okay, we got that covered. Let's talk about horizontal stretches and shrinks, and then we're going to get to do examples. So, horizontal. Well, horizontal, we're multiplying the x by a. Okay, with vertical, we're multiplying the entire function by a. This is horizontal because we're multiplying just the x, what's inside, by a. All right. So I'm not going to be, the question I got earlier, I'm putting a value in here, but I'm not putting a value in here that's a different exponent. All right. I'm not going to, that would change the problem to a totally different extent, which I'm not going to go to in this chapter, but which I will go to in the third chapter. So we got a little while till we get there. So here, my a values, I can put values in that are larger than 1, or I can put values in that are between 0 and 1. So let's put in a value larger than 1 first. Let's say I have, I don't know, y equals 2x squared. Okay? So now this is horizontal because I'm not putting the 2 on the outside like I did before. This 2 is multiplying the x. Okay? So what does this 2 do? Well, 2 is a number bigger than 1, right? 2 is bigger than 1. So I'm going to get a horizontal shrink. This is going to be a horizontal shrink. It's a horizontal shrink, okay, meaning that um, you're going to be moving horizontally is with respect to y. So it actually models the blue graph. A is bigger than 1, it models the blue graph. So as you horizontally shrink, you get closer and closer to the y-axis, which means that you get taller and more narrow, okay? Horizontal shrinks sort of appear like vertical stretches. Okay, there's a relationship that exists there, which we're going to see in a little while. So a horizontal shrink, when you shrink horizontally, you get stretched out vertically. All right, and yeah, there is a relationship between those two items. Okay, if you get shrunken down horizontally, you're going to be stretched vertically. In other words, as you get pulled closer to the y-axis, you're being pulled away from the x-axis. So there is a relationship between them. So for now, if you multiply by a number bigger than 1, you're going to shrink horizontally. You're going to become more narrow and taller. What if we want to do a number that's in between 0 and 1 or smaller? How about something like y equals, I don't know, 1/3 x squared? Okay, that's something that is smaller than 1 and bigger than 0. It's a number that's in between. So when we have a number in between 0 and 1, we're actually talking about a horizontal stretch. And sorry, I didn't have enough space to fit the word horizontal there. So horizontal stretch. So what happens now is horizontally stretching means we move away from the y-axis. We're stretching out away from the y-axis. As we stretch out away from the y-axis, okay, we actually get closer to the x-axis. So it's kind of, again, the same thing. As you stretch out horizontally, you're shrinking vertically. So there's that inverse thing going on there. When you do one, if you stretch out horizontally, you shrink vertically. If you shrink horizontally, you stretch out vertically. That's going to be true, okay, based on just on geometry, okay? I'm going to illustrate this and show you how this works using Desmos so we can see a bunch of different values and see what's going on here. But I do want to show you the, you know what, let me do this first and then I'll connect these two things. So let's take a look at these and see what's happening. Let's go to Desmos and explore it because I want you to see it in practice. Okay, so let me let Desmos load up. Okay, it should be loaded up at this point. I'm going to erase these. I'm just going to leave, I'm going to put the parent function in black. So let me get rid of this. Okay, let's get rid of those. Okay, so there's my parent function, all right? And now I want to see what happens as I change the values that multiply x. So let's take a look at 2x squared. I want it to be a different color. Let's look at 2x squared. Okay, we can see that because we multiplied by a number bigger than 1, we got a horizontal shrink. It's hugging the y-axis more tightly. As I make this number larger, it's going to continue to shrink in the horizontal. Let's try 3x squared. Okay, now the blue one is even hugging the y-axis even tighter. It's shrunken down with respect to y even more. If I do 20x squared, it's going to hug it even more tightly. It's going to be horizontally shrunken even further. And you can see the green one is extremely narrow, right? It's extremely horizontally shrunken down. It's hugging the y-axis really tightly. Okay. So these are all examples of shrinks. The black one is the parent function. The red one's horizontally shrunken down. The blue one's shrunken down even further. And the green one is really shrunken down. Okay. It's really hugging the y-axis really tightly. Now, if I start putting values in that are in between 0 and 1, small values, I should get a horizontal stretch. So let me try doing like a half x squared or something. 1/2 x squared. So you can see that this one is stretched out in the horizontal, okay? Because I used a half. If I do something like a third, it should be stretched out even further because a third is a smaller number. A third x squared. Let's see how that looks. Okay, and now I have another, it's like a black color again. I guess it ran out of colors. So yeah, so this one is stretched out even more. Okay, if I make it a fourth, it should be even more. Make that a 4. Okay, now it's even wider. Okay, you can see I can keep, if I make the number smaller, because 1/4 is 0.25. If I make this, keep making the fraction a smaller valued fraction, it's going to continue to stretch out horizontally. And you'll notice as it stretches out horizontally, it's actually shrinking vertically. You can kind of see that. And I can prove that. Let me show you what I mean. Okay. What I'm going to say here is that 2x squared, if you work that out algebraically, it's 4x. Let me use a different color. Okay, let's do 4x squared. 4x squared. You can see the red and blue. The red and blue are sitting on top of each other. You can't see them anymore because the blue is on top of the red. That's because uh, a factor, a horizontal shrink by a factor of 2 is equal to a vertical stretch by a factor of 4. So this horizontal shrink and this vertical stretch are equivalent. Okay. So we can see horizontal stretches and vertical shrinks horizontal shrinks and vertical stretches are related. And the other way I said it too is also related. Let me take questions. Anything at all on that before I go to examples? Anything?
No.
Nothing? Okay. So let me go to the first two examples. And then I have a couple for you to try by yourself, and then that'll be it for today. All right. So these two examples they want us to describe the transformations of x squared represented by g and graph each. This is exactly like yesterday. Same exact activity, really. All right. So I want to basically let me just plot x squared, the parent function, which is nothing. That's what we did the other day too. We just plotted. We started out by putting what the parent function looks like. That's the wrong place. Let me plot the parent function. Do you have to do this? Actually, you don't have to because you can use the computer to do it for you. But I should have really had the computer do my graph, but I didn't. So I'll have to graph it manually. Okay. So my graph is pretty terrible, but what can I do? I can't. It's hard to draw with the mouse here. Okay, that's the best I can do. I'm sorry. So there's my parent function x squared. It doesn't look too good. I want to see what happens here with negative 1/2 x squared. So I have negative 1/2 x squared. Before, I know that you can just put this in the computer and put this in the computer. This is x squared, by the way. You can drop both of these in the computer and then do a comparison, and that's fine. That's fine. You can describe it based on what you see. But I like to have a little fun with this. I just want to get some predictions. Anybody have any prediction about what they believe will happen in this problem because of the negative 1/2? Any predictions?
Um. Oh, it's gonna reflect.
It's going to reflect.
Yeah.
I agree with that. So prediction, it's going to be reflect. It's going to reflect. I agree with this. Anything else? What do you think the 1/2's going to do? Anybody have any idea what the 1/2's going to do?
Gonna cause a
Vertical shrink.
Vertical shrink. So we're going to see a reflection and a vertical shrink. Let's see if this is the case. And I'm going to write my actual answer underneath the problem after I graph it. So we're predicting here, which is great. I love predicting. We're predicting a reflection and a vertical shrink. Let's see if this prediction is correct. Okay. So I have to plot negative 1/2 x squared, and I have to, and the parent function too. So x squared and negative 1/2 x squared. So let's do that. Okay. So Desmos is loading up. So you should at this point see the parent function x squared, which is in black. Okay. And now I want to plot negative 1/2 x squared. And there it is. So, were our predictions correct? So for those of you who couldn't do this, who didn't get the prediction, that's okay. You can say, oh, here's my original, and here's my new function. Well, based on what I see, I can clearly see that this graph is reflected in the x-axis. I can see it. It's reflected over the x-axis, so that's visible to me. Also, this graph is wider. Okay, it's wider than the parent. Okay. I can see it's wider. So because of that, I can say that well, it's a reflection in the x-axis. I'm just going to write this down, so I can clearly see it's a reflection in the x-axis. Reflection, x-axis. And I also see that this graph is wider. That's because of the 1/2, okay? 1/2 is a number between 0 and 1. So this is a vertical shrink because you have a number between 0 and 1 multiplying the function. So I can just say vertical shrink by a factor of 1/2. So it's a vertical shrink. I'm just writing this down. I'm going to bring you back to notebook in a second. Vertical shrink by factor 1/2. Okay, so let's go back to notebook. Okay, and I put my prediction on the side here, and this is the actual answer here. Okay, what we saw was a reflection in the x-axis, followed by a vertical shrink uh, of a factor of a half. Okay, that's what happened, and I'm going to try to graph this as best I can. The new graph should be a little wider. I don't want to use black ink because I use that for my parent function. So the new function should be wider, and it's going this way, right? This is obviously not scalar. I made it way too wide. Let me just make it a little less wild like that. Shouldn't be that wide. Okay, so it is wider. All right, but something like that. Again, this is just a sketch. Okay, if you want to get the exact point, you can from Desmos and do that. But the answer to this question is really describing the transformation. So this is really the answer. All right, they want the answer in words. The answer really is reflection in the x-axis and a vertical shrink of a factor of a half. So that's the actual answer. Okay, I like doing the prediction part. Um, but if you're not sure, you can do the graph and then write down what you see. That's fine too. All right, we have one more of these. Let's take a look. I'm just going to write down the parent function again for like the general rule for quadratics, which is in the EQ, right? We've seen this a couple of times already. And just to refresh our memory, we know that K is the vertical change. And we know H is the horizontal change. And now we know we learned that A is going to be, it involves stretches and shrinks. Okay, so the A value determines stretches and shrinks. Okay, all right. Anybody want to make a prediction about what's going to happen with the g of x here? I'm just going to quickly plot the parent function, x squared. I just like doing that. Anybody have any predictions about what they think is going to happen?
Horizontal shrink and translation of 1 unit right.
Okay, so I have a horizontal shrink, and I also have, he said, a vertical shift up one, right? A vertical shift. Okay, so let's see if he's right. I have a horizontal shrink, and then I have it's shifted vertically, okay, by 1 unit. So is this going to be a horizontal shrink and vertical and pushed up 1 unit? Let's take a look. Okay, so as Desmos is loading up, I'm leaving x squared in because there's the parent function, which I have graphed on my grid. Okay, I graphed this already. And now I believe it was 2x squared. So 2x and then squared and then plus 1. Okay, so let's examine his claim. The claim that was made is that this is a horizontal shrink and then a translation 1 unit up. Okay, and let's see here. Well, it definitely looks horizontally shrunken to me. You can see that this graph is in the horizontal, it is hugging the y-axis more tightly than the parent is. So it is a horizontal shrink. Okay, it's a horizontal shrink for sure. And it also looks like this graph is shifted up 1 unit. Okay, so it's a horizontal shrink and it's shifted up 1 unit, a translation 1 unit up. So yeah, his claim is correct. It's accurate. That's exactly what's happening. Okay. So if you weren't sure about how he got that claim, you can graph this first and then you can do the analysis and say, oh yeah, this is shrunken down horizontally and it's translated up 1 unit. So that's fine too. All right. And that all bears out based on the values you see here. Okay. This +1 is actually K. So that's why it's up 1 unit. And when you multiply X by a value, you're doing a horizontal change, and we're multiplying X by a value that's bigger than 1. That's a horizontal shrink. Okay. So a horizontal shrink and then a vertical shift. That is correct. He was right. Oops, let me put it back in the notebook. Okay, so I'm just going to make a quick graph of this. It was hugging the y-axis a little more tightly, not drawing to scale. Okay, and my vertex is 0, 1. So I have a horizontal shrink and a vertical shift or vertical translation of 1 unit. Okay, and that's basically it for B. So let's take a look at the other example. Technically, the horizontal shrink, I believe they use the reciprocal factor when they do horizontal, which means that it's a horizontal shrink of really, it's by a factor of a half, but I'm not going to make you write that. I'm just going to write horizontal shrink and then with the fact it's a vertical shift. I don't think you need the factor for that. Some students might change this, by the way, into 4x squared plus 1. And the reason that they do that is because they take the square, 2x times 2x is 4x squared, and then plus 1. But these are actually the same graph, okay? This horizontal shrink is equal to this vertical stretch because they're inversely related, okay? Horizontal shrinks and vertical stretches are there, right? Shrinking horizontally is the same as stretching vertically. Okay, so we don't have a lot of time. Let me just, I don't, you know what? In my other class, I was only able to do 6, and I left 4 and 5 for you guys to work out on your own. And then we'll look at those on Monday. So let's just look at 6. There's only 5 minutes left. It's the same thing we just did, okay? You're gonna work with x squared, and then you're gonna describe the transformation that you get when you do each one of these examples. So I'm only gonna be doing 6. And just so you know, again, I just like listing the general formula up here. I like having this. So there's the general, and I'm doing 6 only because that's all I have time for. So 6 says g of x equals negative x plus 3 squared plus 2. I like this one because this one involves a little bit of everything. It's the stuff that we did yesterday and then a little bit of what we did today. Anybody want to make a prediction about what's going to happen to x squared? I'm just going to plot x squared really quick. I know the time's running out. That looks terrible. It's too V-shaped. I'm trying to fix that. This is going to be hard for me to do because the space I have is so limited. Okay, it's the best I can do. There's my parent function. Anybody want to make a prediction about what's going to happen with G?
A reflection over x-axis and a translation of 3 units left and 2 units up.
So reflection of the x-axis and a translation. He said 3 units left, right? Translation, 3 units left. And he also said 2 units up. Okay. So basically, yeah, what's going to happen here is this actually all looks like it's perfect. The reflection is coming because of the fact that we've negated the function. So this negative, I believe, is what's going to cause the reflection in the x-axis. So this looks like it's going to be right. I'm working along with him to see, and then we're going to actually put it in the computer in a second. We'll see for ourselves. But we learned yesterday that this value controls the horizontal change. So since we're adding 3, that's going to be 3 units left. Okay, that's the horizontal change. And then K is 2. So this plus 2 is going to push the graph 2 units up. So basically, I should be seeing a reflection in the x-axis. It's going to be shifted 3 units left, and then it's going to be shifted 2 units up. So I believe it's going to end here and then go this way, right? Right? Let's see if we're correct. This is the prediction we're making. We're saying it's flipped over, okay, and then it's pushed 3 units left, and then pushed 2 units up. I think this is going to be the case. Let's find out right now by putting this into the computer. So if you're having trouble, no worries. We have access to Desmos, which is going to take care of this for us. So let's find out. Okay, and for some people who didn't see everything that we just did, that's fine too, because you can always do what I'm about to do now. You can say, okay, well, the function's negative x plus 3 squared. Sorry, I don't want to put it in black ink because I want to make a different color. So negative x plus 3 squared, and then plus 1. And look at that. It flipped it over at first. It shifted it 3 units left and 1 unit up. So yeah, it did everything we said it would do. The negative here represents the reflection. The plus 3 represents the movement to the left. And the plus 1 on the outside, that's K, that's the vertical shift up 1 unit. So that's the new function we get with a vertice of negative 3 comma 1. So in my notes, I'm just going to make sure that I put that down. And I have my new negative 3 comma 1. There's my vertice. All right, nicely
Mr.
done.
MPZ,
Yes, yes.
it's negative 3 and 2, not 1.
Oh, sorry. All right. So my mistake. Thank you. So, okay. All that will change is that it's going to be up 2 units instead of up 1 unit. Okay. Sorry about that. So yeah, it's plus 2. My bad. Okay. So it's 3 units left and then 2 units up, which for some reason I graphed properly and just said it wrong. Okay. So 3 units left, 2 units up. All right. That's all I have for today. When you get a chance, just take a look at these two. I'll probably put an assignment up, but that won't be due till Tuesday. Okay. So for now, it's just 4 and 5 I want you to look at for Monday, and that's all. So I'm going to stop here. If there aren't any questions, then please have a great weekend, and please be safe. And I will see you on Monday. Okay.
Okay, bye.
Bye, everybody.
Bye,
Bye.
Mr. MPZ.
Bye.
Take it easy. Good job, everybody.